Welcome back to WizVibes Talks. Get ready to plunge into the Surya Siddhanta, a really mind-blowing ancient Indian text. Think of it as like a cosmic user manual from way back when. It's where the logic of the stars, what they called Vijnan, it beautifully intertwined with deep spiritual understanding, Adhyatma.
Precisely. The Surya Siddhanta, which literally translates to sun treatise, it offers us this extraordinary peek into how ancient scholars observed, understood, and, well, mapped the universe.
Yeah.
Our goal in this deep dive, really, is to explore its fascinating origins,
Right.
unpack its surprisingly accurate astronomical knowledge.
It was just incredible.
It really is. And also trace its historical journey across different cultures and, touch upon the spiritual and philosophical ideas that underpin it all.
Exactly. We've got a stack of, well, fascinating sources that delve into pretty much everything, from creation stories and really intricate math to detailed descriptions of how planets move and their grand cosmological framework. We'll be navigating a timeline stretching from what ancient legends claim are millions of years ago, right up to its lasting influence even today. Okay, so let's get right into it. The Surya Siddhanta. Where did this incredible journey begin?
The traditional story of its origin is truly captivating. According to the Surya Siddhanta itself, this profound knowledge was revealed directly by the sun god Surya.
The sun god himself.
Yes, to an asura named Maya. This mythical event is said to have taken place at the very end of the Satya Yuga. That's the golden age in Hindu cosmology, at a place called Romakapura. If we're going by those ancient timelines, this would place its origin millions of years in the past.
Wow.
And this concept of vast cyclical time, even if it's, mythological in its exact duration, it reveals a really sophisticated understanding of long-term astronomical cycles, quite remarkable for the period.
Millions of years.
Yeah.
That's a pretty epic backstory. But when do historians think this text actually came into being, in its current form?
Right. Well, while the myth points to this immense antiquity, historical scholarship suggests that the Surya Siddhanta, in the form we recognize today, was likely composed or compiled sometime around the 4th to 5th century CE.
Okay.
This was during India's Gupta Empire, which was a real golden age for science and mathematics there. However, it's important to remember that the traditional view considers this knowledge to be much, much older, passed down perhaps through oral tradition,
Right.
and possibly even earlier, now lost texts. There's this idea of it being a living text, meaning it could have been revised, updated, and added to over centuries.
A living text. That's a cool way to think about it. So while folklore gives us Surya and Maya, who do historians think might have been involved in shaping it, any names?
Well, Al-Biruni, who was a brilliant Persian scholar from the 11th century, he mentions that a disciple of the renowned astronomer Aryabhata, named Latadeva, wrote a version of the Surya Siddhanta.
Ah, okay. A link to Aryabhata.
Exactly. Now, whether Latadeva was the sole author or if he compiled existing knowledge, that's still debated. But Al-Biruni's mention is significant because it tells us that by around 500 CE, the Surya Siddhanta was already a well-established and highly regarded astronomical work in India. In fact, Varahamihira, another towering figure in 6th century Indian astronomy, included it as one of the 5 principal astronomical treatises in his Panchasiddhantika,
Siddhantika, right.
which really highlights its importance at that time.
So by the 6th century, it was definitely a major player. Can you paint a picture for us? What exactly is the Surya Siddhanta, like structurally?
Essentially, it's a comprehensive handbook of astronomy and mathematics, written in Sanskrit verse.
In verse, okay.
Yeah, around 500 concise verses spread across 14 chapters. The poetic form made it easier to memorize and transmit, you see. Later scholars wrote prose commentaries to elaborate on the formulas and rules. It firmly belongs to the tradition of Jyotisha, which encompasses Vedic astronomy and astrology, one of the 6 Vedangas, the auxiliary disciplines associated with the Vedas.
The Vedangas, right. Timekeeping for rituals and such.
Primarily, yes. Jyotisha's main focus was on timekeeping for rituals and understanding celestial influences. However, the Surya Siddhanta goes way beyond just calculating auspicious dates. It presents a mathematically detailed model of the solar system as they understood it then, aiming to explain the motions and positions of celestial bodies.
And this detailed knowledge, where did it come from? Were there influences from other ancient cultures, like the Greeks?
This is a really fascinating area of discussion among scholars. There's evidence suggesting potential influences from Hellenistic Greek astronomy, particularly in the use of, say, trigonometric tables.
Trig tables, interesting.
Yeah, the sine tables found in the Surya Siddhanta show parallels with the earlier chord tables developed by the Greek astronomer Hipparchus.
Hipparchus, okay.
But interestingly, The Indian sign tables often demonstrate a greater level of precision. This hints at some level of interaction, or perhaps even independent but parallel development between Indian and Greek astronomy, somewhere between, say, 100 BCE and 300 CE. At the same time, many core concepts are distinctly Indian, like the system of 27 nakshatras or lunar mansions.
Like nakshatras, yeah.
These are like 27 or 28 segments along the moon's orbit used as a celestial backdrop. Think of them like constellations along the ecliptic. And of course, the vast cyclical timescales we've already mentioned, those are a hallmark of Indian cosmology.
So it's a mix, or debated.
It's debated. While some scholars, like David Pingree, have argued for significant Greek influence, perhaps through Indo-Greek interactions. Others, such as Yukio Shashi, they contend for a more independent development, or even the possibility of Indian influence flowing outwards. Ultimately, by the time the Surya Siddhanta reached its definitive form, it seems to have represented a powerful synthesis of careful observation and sophisticated mathematical techniques, drawing perhaps from various sources, but definitely forging its own unique path.
So it sounds like it was both a product of its time and deeply rooted in its own intellectual and cultural landscape. You mentioned an opening prayer. How did this blend of spirituality and rigorous inquiry actually work in the Surya Siddhanta? It seems unusual from a modern perspective.
Well, that's a truly beautiful aspect of the text. The very first verse of the Surya Siddhanta is indeed a prayer, an invocation to Brahman, the ultimate reality in Hindu philosophy.
So it starts right off with spirituality.
Exactly. It immediately sets a sacred tone for the entire work. Furthermore, the knowledge itself is presented as a divine gift, directly revealed by Surya, the sun god, to Maya. This strongly suggests that in ancient India, there wasn't necessarily this sharp dividing line between what we today might call scientific and spiritual pursuits.
They were intertwined.
Precisely. Instead, the movements and patterns of celestial bodies were seen as fundamental expressions of cosmic truth, holding both scientific and profound spiritual significance. The universe could be viewed as a kind of sacred architecture,
Yeah, I see.
And studying astronomy was a way to understand its divine workings, to get closer to the nature of reality itself. So the Surya Siddhanta beautifully embodies both faith and logical reasoning as complementary paths to understanding the universe.
That's a really insightful perspective. Now let's dive into the meat of it. You mentioned 14 chapters. Can you give us a sense of what each one covers? Maybe highlight some of the most interesting bits of each.
Absolutely. The 14 chapters of the Surya Siddhanta systematically unfold the ancient Indian astronomical system. It's quite logical in its progression.
Okay, let's start with chapter 1. What's the big picture there? Madhyadikara, was it?
Yes. Chapter 1, Madhyadikara. That translates roughly to the chapter on mean motions. It lays the foundational groundwork by dealing with the average speeds and orbital periods of the planets. It establishes how long, on average, each planet takes to complete one revolution around the sun. Well, in their geocentric model around the Earth.
Right, geocentric, got it.
And how to calculate their average daily movement. A key concept introduced here is the Mahayuga.
The Mahayuga, that huge time cycle.
Exactly, a vast cycle of 4,320,000 years. This enormous time frame was used to achieve incredible precision when calculating the very small fractional motions of celestial bodies over long periods.
Makes sense. You need a big denominator for tiny fractions.
Precisely. For example, it states the sun completes exactly 4,320,000 revolutions within one Mahayuga. This chapter also meticulously defines various units of time, ranging from the smallest unit, the prana, which is related to a breath,
Wow.
all the way up to the year, which is interestingly described as one day of the gods.
The day of the gods, huh?
And finally, it introduces the famous four Yuga, Satya, Treta, Dvapara, and Kali, and their combined duration of 4.32 million human years. The chapter even concludes by emphasizing the spiritual rewards that come from mastering the knowledge of astronomy.
Okay, so it's setting the stage with these fundamental cycles and average movements. What happens in chapter 2 then? Sphutagati.
Chapter 2, Sphutagati, which you could translate as the chapter on two motions. This moves beyond those averages to tackle the more complex reality of planetary movement. Because, as ancient astronomers knew, planets don't move at a perfectly uniform speed.
Right, their orbits aren't perfect circles.
Exactly. This chapter introduces various correction factors to adjust the mean positions calculated in the first chapter to find the planet's true, instantaneous positions in the sky. It explains how to account for the varying speeds, including the phenomenon of retrograde motion.
Where they seem to go backwards.
Yes, where a planet appears to move backward against the starry background. The Surya Siddhanta uses sophisticated mathematical techniques, including concepts analogous to the epicycle theory developed in ancient Greece,
Epicycles.
though implemented here with precise sine functions to model these irregularities. This chapter really highlights a sophisticated level of astronomical modeling for its time.
Moving on, what does Chapter 3 have in store for us? Trip Prashna. 3 questions.
Exactly. Chapter 3, Trip Prashna, focuses on what we might think of as terrestrial coordinates and practical timekeeping. Trip Prashna literally refers to 3 key questions: direction, place, and time. This chapter describes in detail the methods for constructing a sundial, known as the Triprashna Yantra, using a vertical rod called a gnomon, or Shankuyatra.
A gnomon, like the pointy bit on a sundial.
Precisely that. It explains exactly how to use the shadow cast by this gnomon to determine local noon, the cardinal directions, north, south, east, west, and even the observer's latitude on Earth. It really emphasizes the fundamental connection between observing the heavens and understanding our place and time here on Earth. It mentions concepts like latitude, aksha, longitude, descentara, offers intriguing hints about calculating Earth's circumference, and references the celestial sphere.
Very practical.
It also touches on methods for finding directions at night, possibly using the pole star, which they called Dhruvatara.
Sounds incredibly useful for navigation in daily life. What celestial event takes center stage in Chapter 4? Chandragrahan, lunar eclipse.
Spot on. Chapter 4, Chandragrahan, dives into the intricacies of calculating when and where lunar eclipses will occur. It meticulously explains the necessary alignment: sun, earth, moon, in that order.
Sun, Earth, Moon. Got it.
Importantly, it introduces the concept of the lunar nodes, the points where the moon's orbit crosses the Earth's orbital plane around the sun. And it personifies them as the shadow entities Rahu and Ketu.
Rahu and Ketu, I've heard of them, the nodes.
These ascending and descending nodes, yes. The chapter details how to calculate the size and shape of the Earth's shadow, the umbra and penumbra, and precisely how the moon passes through it. It even provides formulas for calculating the eclipse's half duration and the exact moments of first and last contact. This demonstrates the remarkable ability of ancient Indian astronomers to not just observe, but to predict these celestial events with considerable accuracy.
Okay, predicting lunar eclipses. And what about the other kind? Chapter 5, I presume? Surya Grahan?
Exactly. Chapter 5, Surya Grahan and Parallax, tackles the calculation of solar eclipses, which, as you know, happen when the moon passes directly between the Earth and the sun, casting its shadow on Earth. A key element introduced in this chapter is the concept of parallax.
Parallax, right, the apparent shift in position.
Yes, like holding your thumb up and looking with one eye then the other. That apparent shift. On a cosmic scale, this chapter explains how the observer's specific location on Earth affects the apparent position of the sun and moon.
Ah, so where you are matters for a solar eclipse.
Critically, it explains how to account for this parallax when calculating the timing and visibility of a solar eclipse. It details how to calculate the moon's shadow cone and determine whether an eclipse will be total or partial for a given location. It also covers computing the true shadow and contact points. The use of spherical geometry in these parallax calculations underscores their sophisticated understanding of celestial mechanics and the difference between geocentric, Earth-centered, and topocentric observer-centered positions.
Chapter 6 has a rather visual-sounding title, Projection of Eclipses. Granakranti.
You're right. Chapter 6, Projection of Eclipses, Granakranti, seems to focus on methods for visually representing the different phases of an eclipse. It likely describes techniques for, say, drawing the circles of the sun and moon to scale and then marking their overlap to illustrate how the eclipse progresses.
So, like diagrams.
Exactly. A practical way to understand and communicate the geometrical aspects of the calculations. It might also discuss the graphical representation of the eclipse's half duration and its magnitude. It's sort of a visualization toolkit for understanding these events.
Chapter 7 shifts our focus back to the planets. Planetary conjunctions.
Chapter 7, Planetary Conjunctions, deals with predicting when different planets will appear very close to each other in the sky. These are called conjunctions. It involves calculating the positions of the various planets over time and determining when their celestial longitudes become the same or very similar.
Finding when they line up, basically.
Yeah, pretty much. The concept of synodic periods, the time it takes for two planets to return to the same relative position as seen from Earth, becomes important here. The chapter may also touch upon instances of multiple planets appearing close together or planets aligning with specific bright stars or nakshatras. And it's likely these conjunctions also had astrological interpretations in their worldview.
Makes sense. Chapter 8 sounds like a celestial map, star constellations, nakshatra sthiti.
Exactly. Chapter 8, Star Constellations, Nakshatra Sthiti, provides detailed information about the positions of the 27 or 28 nakshatras, those lunar mansions we talked about earlier. It likely lists the celestial coordinates or other defining characteristics of the most prominent stars within each nakshatra, essentially serving as a star catalog within the Indian sidereal coordinate system.
Sidereal, meaning based on the stars.
Yes, a system that anchors celestial positions to the fixed background stars rather than the moving sun. This chapter was fundamental for calendar calculations and for determining auspicious times for Vedic rituals, based on the moon's position relative to these nakshatras. It also shows the close relationship between their astronomy and astrological practices.
Okay. What about the visibility of stars and planets? That sounds like Chapter 9. Heliacal risings and settings.
You've got it. Chapter 9, Heliacal Risings and Settings, explains how to calculate the moments when planets and stars first become visible at dawn after being hidden by the sun's glare,
Heliacal rising. Okay.
and when they last remain visible at dusk before disappearing into the sun's light, which is the heliacal setting. Determining these moments involves considering a planet's or star's orbit relative to both the sun and Earth, plus visibility criteria against the twilight sky. This was crucial for calendrical purposes in many ancient cultures. For instance, the heliacal rising of bright stars like Sirius, associated with Mrigashira in India, often marked important agricultural seasons.
Chapter 10 seems to zoom in on our nearest celestial neighbor, the moon.
Chapter 10. The moon's phases and rising times focuses specifically on the moon. It details how to calculate the tithi, or lunar day in the Hindu calendar, and the changing shape of the moon's illuminated portion as it cycles through its phases. It explains the understanding that the moon shines by reflected sunlight and how the angle between the sun, moon, and Earth determines its appearance.
The geometry of phases.
Exactly. The chapter also provides rules for finding the celestial longitude of the moon's cusps, the points of the crescent moon, and covers predicting moonrise and moonset times, noting how these vary compared to the sun's movements. This chapter was absolutely essential for constructing the lunar-based Hindu calendar. And it's worth noting again, the incredibly precise value for the synodic month, the time between two new moons provided in the Surya Siddhanta. Really remarkable.
Chapter 11 sounds like an interesting mix. Miscellany, eclipses, omens, and astrology, so it's not all pure astronomy.
Chapter 11, Miscellany. Eclipses, omens, and astrology is indeed a fascinating blend. It mixes precise astronomical calculations with astrological interpretations and the belief in omens associated with celestial events. It discusses inauspicious time periods thought to arise due to specific positions of the sun and moon, and gives examples of astrological meanings attributed to eclipses, halos around the sun or moon, certain combinations of tithys and weekdays.
So applying the astronomy to predictions or omens.
Right. The chapter provides computational rules for identifying and interpreting these phenomena. It really served as a bridge between the observational astronomy of the time and the practical applications used by astrologers in predicting earthly events and determining auspicious times. It even mentions concepts like yogas, karanas, muhurtas, auspicious time intervals, and other atmospheric phenomena that might be linked to solar or lunar activity, though maybe not in a purely scientific sense as we'd understand it today.
Chapter 12 sounds like it broadens our view right back out to the entire cosmos. Cosmology and geography, Bhuvana Kosha.
Chapter 12. Cosmology and Geography, Bhuvana Kosha, definitely takes a step back. It addresses the creation of the world and the overall structure of the cosmos as envisioned in the Surya Siddhanta. It touches upon mythological creation stories, including the concept of Brahma's day and night, the Kalpa. But crucially, it also asserts that the Earth is a sphere bhugola.
A sphere. That early.
Yes. And astonishingly, this chapter provides a calculation for the Earth's diameter that is remarkably close to modern measurements around 8,000 miles compared to the modern equatorial diameter of about 7,926 miles.
Wow, that's incredibly close.
It really is. It also includes estimates for the moon's diameter and its distance from Earth that, while maybe not as precise as the Earth's diameter, are still within a reasonable range given their observational limits. Furthermore, it notes the Earth's axial tilt, the obliquity of the ecliptic, and even makes an intriguing reference to a north and south pole star being visible at the equator around 3000 BCE, suggesting an awareness of the slow changes in the Earth's axial orientation over vast periods.
Precession again.
Seems like it. Finally, it places the cycle of yugas within this grand cosmological framework, emphasizing the vastness of the kalpas and the cyclical nature of cosmic time.
Okay, chapter 13 brings us down to Earth, or at least to the instruments they use to observe the heavens, instruments and observations.
Exactly. Chapter 13, Instruments and Observations, shifts the focus to the practical tools, the yantras, that ancient Indian astronomers used to make their observations. It describes various instruments, including the armillary sphere or Galayantra.
The armillary sphere, right? That model of the sky.
Yes, a model of the celestial sphere used for locating celestial objects. It also mentions other devices like the chakrayantra, a disc instrument, golyantra, a globe instrument, different types of shadow instruments, including the gnomon we mentioned.
The Shankyatra.
Right, and even water clocks for precise timekeeping. The chapter details the construction and use of the armillary sphere, explaining how its rings and pointers could be aligned with celestial objects to measure their positions. It also mentions simpler instruments like the gnomon and a semicircular protractor, the Dhanur yantra, used for measuring angles. This chapter really underscores the empirical basis of their astronomical knowledge and highlights the ingenuity of these early observers.
And to wrap it all up, chapter 14 deals with the fundamental concept that underpins all of astronomy, time itself. Different kinds of time.
You got it. Chapter 14, Different Kinds of Time, provides a comprehensive overview of the various systems of time measurement used in ancient Indian astronomy. Solar time, sidereal time, based on the stars, lunar time, and civil time, our everyday measure. It carefully explains the distinctions between a sidereal day, Earth's rotation relative to stars, a solar day based on the sun, a lunar day, the Tithi, and the civil day.
Lots of different days.
Indeed. The chapter also delves into larger cycles, like the difference between the sidereal year, sun relative to stars, and the tropical year, time between seasons, basically.
Which is the one our calendar uses.
Mostly, yes. The tropical year determines our seasons. It also discusses the concept of intercalary months ad hic massa to reconcile the lunar and solar calendars, and mentions different calendrical eras used in India. Notably, this chapter presents an incredibly accurate stated length for the tropical year. It concludes by emphasizing the cyclical nature of time, with smaller cycles nested within larger ones, and this holistic understanding of kala, or time, as a fundamental aspect of the cosmos.
That's an incredibly detailed tour through the Surya Siddhanta. It's just astonishing how much ground they covered. Now let's get to something truly remarkable you hinted at earlier. The often surprising alignment between some of the values presented in the Surya Siddhanta and modern scientific measurements.
This is where the text really continues to fascinate researchers. The level of precision they achieved in some calculations, especially when you consider the limitations of their ancient observational tools. It's nothing short of extraordinary.
Let's start with something fundamental. The shape and size of our own planet. They really said it was a sphere.
As we mentioned, yes, the Surya Siddhanta clearly describes the Earth as a sphere, Golakar, and it provides that quantified diameter of around 8,000 miles.
Which is just over 1% off the modern polar diameter.
Exactly, around 7,900 miles modernly. The difference is incredibly small. From this diameter, they also inferred a circumference of roughly 25,000 miles, which again is remarkably close to the modern equatorial circumference of around 24,901 miles.
That understanding, centuries before it was common knowledge in the West, is just wow.
It truly is significant.
What about the distances within our Earth-Moon-Sun system? How did they fare there?
Well, the Surya Siddhanta gives the moon's distance from Earth as approximately 258,000 miles. The modern average is about 238,000 miles. So it's in the right ballpark, especially considering the moon's orbit isn't perfectly circular.
True, the distance varies.
Their estimate for the moon's diameter is around 2,400 miles, compared to the modern value of about 2,060 miles. Again, reasonably close. Regarding the sun, while the text doesn't give a precise distance in miles as we'd think of it, it clearly recognized the sun as being vastly farther away than the moon and incredibly large. One verse even implies a diameter for the sun that is 108 times that of the Earth.
108 times. What's the modern value?
Closer to 109 times. So, surprisingly accurate ratio. It shows a remarkable grasp of the relative sizes and distances involved.
And the length of our year. This is always a point that amazes people. How accurate were they?
Incredibly accurate. The Surya Siddhanta's calculation for the length of the sidereal year sun relative to the stars is about 365 days, 6 hours, 12 minutes, and 36.6 seconds.
And modern.
Modern measurement is approximately 365 days, 6 hours, 9 minutes, and 10 seconds. That's a difference of only about 3 minutes.
Just 3 minutes.
But perhaps even more astonishing is their calculation for the tropical year, the one that governs our seasons.
Yeah.
They arrived at a value that is only about 1.4 seconds different from the modern value of 365.2422 days.
1.4 seconds.
Yes. To put that in perspective, the Gregorian calendar, which most of the world uses today, actually accumulates a larger error over centuries than the Surya Siddhanta's calculation for the tropical year.
That's just incredible precision. What about the orbital periods of other planets they knew about? Did the accuracy hold up?
It did, remarkably so. The accuracy extends to the orbital periods of other planets visible to the naked eye. For Saturn's orbital period, the Surya Siddhanta calculates around 29.46 years.
And modern.
Modern value is 29.457 years. Very close. Similarly, for Jupiter, they calculated an orbital period of about 11.86 years. The modern value is 11.862 years.
Spot on, practically.
Pretty much. Even for the moon's own orbital periods, its sidereal period relative to the stars and its synodic period between new moons, the values given in the Surya Siddhanta are within mere seconds of modern measurements.
And they were even aware of that slow wobble of the Earth's axis, the precession of the equinoxes, Ayana-Chalan.
Yes, the Surya Siddhanta acknowledges the precession of the equinoxes, which is a very subtle and long-term astronomical phenomenon. Their stated value for this precession was 54 arcseconds per year, resulting in a cycle of approximately 24,000 years.
How does that compare?
It's slightly different from the modernly accepted value of around 50.3 arcseconds per year, which leads to a cycle of about 25,771 years. But the fact that they identified and attempted to quantify this very slow shift in the Earth's rotational axis thousands of years ago is a testament to their keen observation and sophisticated understanding.
And we can't forget their foundational contributions to mathematics, particularly trigonometry, which powered all this.
Absolutely not. The Surya Siddhanta is credited with early and sophisticated use of sine Jaya and cosine Koja functions. They developed sine tables that were remarkably accurate and closely matched modern values for many angles. Furthermore, the text demonstrates the use of algebraic calculations and various approximation methods, showcasing a high level of mathematical sophistication that was essential for their astronomical computations.
And you mentioned it held its own against Western texts.
Right. It's worth remembering that in some aspects, the accuracy of the Surya Siddhanta's astronomical parameters was comparable to or even surpassed that of Ptolemy's Almagest, which was the leading astronomical text in the Western world for over 1,000 years.
It's important to keep in mind, though, as you said, that their underlying understanding of the cosmos was geocentric, right? Earth-centered.
That's correct. Like the vast majority of ancient astronomical systems around the world, the model presented in the Surya Siddhanta is geocentric. It places the Earth at the center with everything else revolving around it. It's important to remember this context when appreciating their achievements, especially considering that the heliocentric model, with the sun at the center, wasn't proposed in India until later by Aryabhata.
Right, different models, but amazing calculation within their model. Finally, those incredibly vast cosmic timescales they describe the Yugas and Kalpas. Do they have any resonance with modern science, even metaphorically?
It's fascinating, isn't it? The concept of a day of Brahma, or Kalpa, being 4.32 billion years is particularly striking when we consider that the scientifically estimated age of the Earth is around 4.54 billion years.
Very close.
And the age of the universe around 13.8 billion years. While the Surya Siddhanta's framework is embedded in mythology and a cyclical view of creation and destruction, the sheer magnitude of the timescales they envisioned is remarkably close to some of the major epochs recognized by modern cosmology. It suggests a deep contemplation of cosmic time that, while different in its philosophical underpinnings, certainly touches upon the immense timescales that modern science also grapples with.
It's truly humbling to see these alignments across millennia. Now, let's turn our attention to some of the historical anecdotes that highlight the Surya Siddhanta's journey and influence through time. It wasn't just a static text, right?
Not at all. The historical impact of the Surya Siddhanta is profound and long-lasting. It shaped astronomical thought and practice for centuries, not only within India, but also influencing intellectual developments in other parts of the world.
We touched on Varahamihira earlier. Can you elaborate on his role in cementing its status?
Yes, Varahamihira's inclusion of the Surya Siddhanta as one of the 5 key astronomical treatises in his Panchastattantika in the 6th century CE. That's a very early and significant indicator of its importance and widespread recognition within India's scientific community at that time. By placing it alongside other influential texts like the Pulisha and Romaka Siddhantas, which are thought to have had some Hellenistic influences, he clearly established the Surya Siddhanta as a central pillar of Indian astronomical knowledge.
And what about Aryabhata and his school of thought? Were they in agreement with the Surya Siddhanta, or was there debate?
Aryabhata, who was a contemporary or perhaps slightly later, had some significant differences in his astronomical model. Most notably, as we mentioned, he proposed that the Earth rotates on its axis.
Which the Surya Siddhanta didn't.
Correct, a concept not found in the Surya Siddhanta's geocentric framework. While they differed on this fundamental point, both the Surya Siddhanta and the Aryabhatiya school were highly influential. Later scholars often referenced and drew upon both traditions. For instance, Brahmagupta, in the 7th century, he critiqued aspects of Aryabhata's model while also acknowledging the importance of the Surya Siddhanta. It shows an ongoing intellectual dialogue and exchange of ideas between these different astronomical traditions.
Then we have Bhaskara II, centuries later, in the 12th century. How did he build upon this foundation?
Bhaskara II. He was one of the most brilliant mathematicians and astronomers of medieval India. His magnum opus, the Siddhanta Suryamanī, is essentially a comprehensive successor to earlier Siddhantas, including the Surya Siddhanta. He built upon the foundations laid down by earlier texts, refining calculations, developing new mathematical tools, and updating astronomical parameters based on his own observations and theoretical work.
So, refining and improving.
Exactly. There's a fascinating anecdote about him accurately predicting a close approach of the planet Mars, which highlights the continued practical application and advancement of the astronomical methods that had their roots in texts like the Surya Siddhanta.
It's remarkable that this knowledge even made its way beyond India to the Arabic-speaking world. How did that happen?
Indeed. During the 8th and 9th centuries, at the height of the Abbasid Caliphate's golden age of science in Baghdad, the Surya Siddhanta was translated into Arabic under the title Sindhind.
Sindhind, okay.
This translation became a foundational text for Islamic astronomy. It influenced the work of many prominent scholars, including Al-Khwarizmi, whose work on algorithms is still fundamental today, and Al-Biruni, whom we mentioned earlier, who also translated it.
And this influenced Europe eventually.
Yes, the transmission of mathematical concepts like the sine function, the Sanskrit jia, became jade in Arabic, and later was mistranslated into the Latin sinus, made its way to Europe through these Arabic texts. It ultimately played a crucial role in the development of Western mathematics and astronomy.
From jaya to sinus. Amazing.
Some historians even speculate that the ideas contained within the Sindhind may have indirectly influenced Nicholas Copernicus centuries later during the Renaissance.
And it continued to hold importance within India itself for centuries after that.
Oh, absolutely. The Surya Siddhanta remained a central text within India's astronomical tradition. It formed the basis for numerous regional astronomical manuals and commentaries written by scholars like Paramasvara in Kerala and Kamalakara in the 17th century. They further elaborated on its principles and refined its calculations. Even today, the Surya Siddhanta continues to be a key source for the calculations used in traditional panchangs.
The Hindu almanacs.
Exactly, which are still widely used for determining auspicious dates, festivals, eclipse times, and other important timings.
Even in more recent times, like the 18th century, it had a resurgence of interest, didn't it, with Jo Singh?
Yes, particularly in the 18th century with Maharaja Sawai Jai Singh II, the founder of Jaipur. He was a keen astronomer and built those famous Jantar observatories.
The Jantar Mantars, right.
Yeah.
Giant instruments.
Exactly. Jai Singh was deeply interested in both Indian and European astronomy. He meticulously compared the astronomical tables based on Indian Siddhantic traditions, including the Surya Siddhanta, with contemporary European tables like those of the French astronomer Philippe de la Hire. While he recognized the advancements made in Europe, he also had a strong belief in the accuracy and observational techniques of Indian astronomy. He commissioned the creation of updated astronomical tables, like the Siddhanta Sarvabhauma and the Samrat Siddhanta, which were rooted in the principles of the Surya Siddhanta and other classical texts.
So he tried to synthesize and update. And what happened when Western scholars encountered this knowledge during the colonial era? Was it accepted? Ignored?
Well, the encounter of European scholars with texts like the Surya Siddhanta during the British colonial period sparked considerable interest and debate. Scholars like John Playfair were genuinely astonished by the accuracy of some of the astronomical parameters and the antiquity claimed for these texts. It led to discussions about their origins and potential influences.
But not everyone was convinced.
No, there were also skeptical voices, like John Bentley, who questioned the originality and age of these works. It became quite a debate. The first comprehensive English translations of the Surya Siddhanta in the 19th century by Pandit Bapudeva Sastri and the Reverend Ebenezer Burgess were crucial. They made the text accessible to a wider international audience, revealing its complexity and prompting further scholarly investigation into its historical context, mathematical sophistication, and scientific achievements.
And its legacy continues to this day in modern India, doesn't it? It's not just a historical artifact.
Absolutely not. The Surya Siddhanta continues to have a cultural presence in India. Its principles are still used in the calculation of traditional panchangs, dictating the timing of festivals and providing eclipse forecasts in almanacs. The text's concept of vast Yuga cycles also continues to influence certain aspects of Hindu philosophical thought. And with a growing interest in India's ancient scientific heritage, the Surya Siddhanta is often highlighted in museums, educational initiatives, and discussions about the history of science. It serves as a powerful reminder of India's rich contributions to astronomy and mathematics.
It's truly an incredible journey of an ancient text through history, influencing scientific thought across continents and centuries. Now let's delve into the spiritual and philosophical undertones that are so deeply woven into the fabric of the Surya Siddhanta. It's not just numbers, is it?
Not at all. Beyond its scientific and mathematical rigor, the Surya Siddhanta offers profound insights into the ancient Indian worldview, particularly its understanding of time, the cosmos, and the relationship between the observable universe and, well, the divine.
The concept of cyclical time with the Yugas and Kalpas seems to be a central philosophical idea here. Can you unpack that a bit more?
Yes, it's absolutely central. The Surya Siddhanta's intricate framework of Yugas, the Satya, Treta, Dwapara, and Kali, forming progressively shorter cycles that then culminate in an enormous kalpa, or a single day in the life of Brahma, spanning billions of years. It presents this grand cyclical view of time. This isn't just about astronomical cycles. It's deeply intertwined with philosophical concepts of cosmic evolution, karma, and rebirth on an immense scale.
So our lives, our history, are just small parts of a much bigger cycle.
Exactly. The text even specifies the start date of the current Kali Yuga, linking a mythological epoch to a specific astronomical configuration. This cyclical perspective offers a powerful understanding of the impermanence of our current age within a much vaster cosmic drama. It suggests that creation and destruction are ongoing processes in an endless cycle.
And the way the text frames knowledge itself as a divine gift, how does that influence its philosophical outlook? You mentioned the opening prayer.
Right. The Surya Siddhanta's opening with a prayer to Brahman and its portrayal of astronomical knowledge as being directly revealed by the sun god Surya to Maya. It underscores a philosophical viewpoint where the pursuit of knowledge, particularly knowledge about the cosmos, is seen as a sacred endeavor. It suggests that understanding the universe is not just a matter of intellectual curiosity, but a way to connect with the divine order and the fundamental truths of existence.
So science is a spiritual path, in a way.
In that view, yes. It aligns with the broader Indian philosophical tradition, where rigorous inquiry and spiritual seeking are often seen as complementary paths to enlightenment. The act of studying the heavens could itself be considered a form of spiritual practice, a tapasya, or disciplined effort to understand the divine workings of the universe.
It also sounds like the text beautifully integrates cosmology with elements of mythology, like Mount Meru.
Absolutely. The Surya Siddhanta seamlessly blends descriptions of the Earth and the cosmos with mythological elements, such as the mention of Mount Meru as a central axis and the division of the Earth into Jambudvipa and other mythical continents. This reflects a philosophical approach that seeks to find correspondences between the macrocosm, the vast universe, and the microcosm, the human experience, and the earthly realm.
As above, so below, kind of.
Very much that kind of thinking. It suggests a holistic worldview where the physical and spiritual are not separate but interconnected aspects of a single reality, and where understanding the structure of the cosmos can provide insights into the nature of existence itself.
The eternal motion of the celestial bodies must have also carried philosophical weight, right? The constant cycles.
Indeed. The constant, predictable motion of the planets and stars likely reinforced philosophical ideas of impermanence, or anitya, the understanding that nothing in the material world lasts forever.
Everything changes.
And also the cyclical nature of existence, samsara, the endless cycle of birth, death, and rebirth. The regularity and orderliness of celestial movements could be seen as a manifestation of cosmic law, or raita, the fundamental principle of natural and moral order that governs the universe. Observing this celestial order might have inspired a sense of harmony and interconnectedness within the larger cosmic framework.
You also mentioned the significance of transitional periods, those Yuga sandhis, the twilight zones between ages.
Yes, the junctures or transitional periods between the yugas, known as Yuga Sandhis, were considered particularly significant times. They were often characterized by upheaval and change, but also seen as holding unique spiritual potential.
Turbulent but potent times.
Exactly. These periods were seen as liminal spaces, marking the end of one cosmic era and the dawn of another. This concept has influenced later philosophical and astrological speculations about the nature of time and the potential for both challenges and spiritual growth during these transitional phases, including, ongoing discussions about the end of the current Kali Yuga.
The sheer scale of measurement in the Surya Siddhanta, from the tiniest fraction of a second to billions of years, that also seems philosophically significant.
It really does. The text's encompassing range of time and spatial scales, from the smallest imaginable fractions, nivoya, to the unimaginable vastness of kalpas, reflects a fascinating sense of scale invariance, like fractal patterns. It suggests an underlying unity of principles governing phenomena across vastly different magnitudes. The very act of quantifying reality with such precision implies a deep belief in the knowable nature of the universe and the power of human intellect to unravel its mysteries.
The numbers themselves might have meaning too, like 108.
Quite possibly. The recurring use of significant numbers like 108 in various calculations hints at deeper symbolic and perhaps even mystical meanings embedded within the seemingly purely mathematical framework.
It sounds like studying the Surya Siddhanta was intended to be more than just an intellectual exercise. It was perhaps meant to cultivate a sense of awe and wonder at the universe.
Absolutely. I think the Surya Siddhanta seems designed to evoke what we might call chamadkar bodh, a profound sense of wonder and astonishment at the intricate workings of the cosmos. It beautifully intersects bhakti, or devotion to the divine, with viveka, or rational inquiry and discernment. The sun itself is revered as both a powerful deity and a physical body whose movements and characteristics are meticulously studied through mathematics.
The divine and the physical together.
Exactly. This embodies the ancient Indian philosophical view of science and spiritual wisdom as not being in conflict, but rather as complementary pathways to understanding the ultimate nature of reality.
It's a powerful and holistic worldview. So in modern times, how is the Surya Siddhanta viewed and revered? What's its lasting legacy today?
Well, the Surya Siddhanta endures as a powerful and highly revered symbol of India's ancient scientific and intellectual achievements. It stands as a foundational text that continues to exert influence, particularly, as we've said, on traditional calendar systems like the Panchanga.
Still used daily by many.
Right, which are still widely used for religious and cultural purposes. It reinforces the enduring cultural understanding that scientific inquiry and spiritual understanding are not mutually exclusive, but can indeed be complementary paths to knowledge. The text serves as a vital showcase of India's rich and sophisticated scientific heritage, inspiring a sense of pride and connection to the intellectual accomplishments of the past.
And inspiration for today.
Definitely. The dedication and profound knowledge of the ancient scholars who preserved and advanced this knowledge continue to be a source of deep respect and inspiration. Now, while it's sometimes mentioned in discussions surrounding lost knowledge or ancient advanced civilizations,
Right, those theories.
it's important to approach those claims with a critical perspective grounded in historical and archaeological evidence. Regardless of such speculative discussions, the documented lineage of teachers and students who diligently preserved and transmitted this knowledge over centuries is deeply respected within traditional scholarly circles. Today, there are renewed efforts to honor the legacy of the Surya Siddhanta in educational curricula and public outreach initiatives. It's recognized for its significant contribution as an early and remarkably accurate chapter in humanity's ongoing exploration of the universe.
It's an incredible story of an ancient text that continues to resonate and inspire, blending math, observation, myth, and philosophy. What a truly deep dive into the Surya Siddhanta. Thank you so much for shedding such insightful light on this fascinating subject.
My pleasure entirely. What's truly captivating, I think, is the enduring human quest to understand our place within the vastness of the cosmos. It's a quest that the Surya Siddhanta so eloquently and meticulously embodies.
Now, we would absolutely love to hear from you, our listeners. What are your thoughts and reactions to this deep dive into the Surya Siddhanta? Did any of its surprisingly accurate insights, its blend of science and spirituality, or perhaps its journey through history particularly resonate with you? Please share your comments and questions. We're always eager to hear your perspectives and continue the conversation. And if this exploration into ancient wisdom sparked your curiosity, please like, share, comment, and subscribe WizVibes YouTube channel for more interesting talk shows.